Coastal Erosion Monitoring, Tools and Techniques. Title: Coastal Erosion Monitoring, Tools and Techniques. Introduction. Coastal erosion is a natural process that affects many coastal areas worldwide. As sea levels rise and storms become more frequent and intense, understanding and monitoring coastal erosion has become increasingly important. By identifying vulnerable areas and assessing erosion rates, scientists and policymakers can develop effective management strategies to mitigate the impact of erosion. In T.'s article, we will explore various tools and techniques used in coastal erosion monitoring and their role in promoting sustainable coastal development. 1. Remote sensing. Remote sensing plays a crucial role in monitoring coastal erosion over large areas. Satellites equipped with remote sensing instruments capture high-resolution images that allow scientists to observe changes in shoreline position, vegetation cover, and sediment distribution. These images provide valuable data for assessing erosion rates and identifying areas at risk. Remote sensing techniques, S. UCHA synthetic aperture radar, SAR, and light detection and ranging, LiDAR, are instrumental in capturing detailed information about coastal landscapes. 2. Global Positioning System, GPS. GPS technology has revolutionized coastal erosion monitoring by providing accurate positional information. By installing GPS receivers at coastal sites, researchers can track the movement of shoreline boundaries and measure erosion rates over time. GPS also allows for the precise positioning of monitoring instruments, such as wave and tide gauges, enhancing data collection and analysis. 3. Ground Penetrating Radar, GPR. Ground penetrating radar is a powerful tool for studying coastal erosion by revealing subsurface features and changes in sediment composition. It uses electromagnetic waves to investigate the subsurface characteristics like sediment layer thickness and structure. By analyzing GPR data, scientists can create detailed cross-sectional images of coastal landforms and detect potential erosion indicators, such as subsurface cavities or water intrusion. 4. Hydrodynamic models. Hydrodynamic models simulate the movement of water and sediment in coastal areas. These models are essential for understanding the dynamics of coastal erosion and its driving forces, such as tides, waves, and currents. By inputting data regarding wave characteristics, sediment transport, and coastal topography, researchers can predict erosion patterns and identify areas prone to erosion. Hydrodynamic modeling allows for more precise and targeted coastal management strategies. 5. WAVs and drones. Unmanned aerial vehicles, WAVs, and drones have emerged as invaluable tools for capturing high-resolution imagery of coastal areas. Equipped with advanced cameras and sensors, WAVs can collect data in real time, allowing for frequent monitoring of erosion hotspots. The high-resolution images captured by WAVs provide detailed information on coastal changes that were previously difficult to observe. WAVs also offer cost-effective alternatives to traditional aerial surveying, enabling more efficient and frequent monitoring of erosion-prone coastal regions. 6. Acoustic Doppler systems. Acoustic Doppler systems are widely used for measuring water velocities and sediment transport in coastal areas. Sensors placed on the seabed or buoys emit sound waves, which bounce off sediment particles and moving water columns. By analyzing the Doppler shift of the reflected waves, scientists can calculate current velocities and sediment movement. Acoustic Doppler systems are crucial for QAN. Defying sediment transport rates, identifying erosion-prone areas, and understanding the mechanisms behind coastal erosion. 7. In situ monitoring. In addition to remote sensing and modeling techniques, in situ monitoring plays a crucial role in coastal erosion assessment. This involves installing instruments directly on the coastline to measure various parameters, such as wave energy, sediment movement, and shoreline changes. For example, wave and tide gauges provide real-time data on wave height, period, and direction, helping researchers understand the forces influencing erosion. Sediment traps and coring devices collect samples of sediment for analysis, aiding in the study of sediment transport and composition. In situ monitoring provides data that complements and validates findings obtained through remote sensing and modeling, enhancing the accuracy and reliability of erosion assessments. 8. Community engagement. An essential aspect of coastal erosion monitoring is community engagement. Local communities often have valuable knowledge and insights about shoreline changes and erosion impacts. By involving the community in monitoring initiatives, scientists and policymakers can benefit from local knowledge and ensure that management strategies are inclusive, effective, and sustainable. 9. Artificial intelligence, AI, and machine learning. Advancements in artificial intelligence and machine learning offer exciting opportunities for coastal erosion monitoring. AI algorithms can analyze large datasets collected through remote sensing, in situ monitoring, and modeling to identify patterns and predict future erosion trends. Machine learning techniques enable automated data processing, improving the efficiency and accuracy of erosion assessments. AI-powered systems can also integrate multiple sources of data to generate comprehensive erosion maps and forecasts, assisting in decision-making processes for coastal management. 10. Long-term monitoring networks. Establishing long-term monitoring networks is essential for tracking coastal erosion over extended periods. These networks consist of a network of monitoring stations strategically placed along vulnerable coastlines. These networks also enable researchers to analyze erosion trends and evaluate the effectiveness of erosion management strategies implemented over time. 11. Citizen science. Citizen science initiatives have become increasingly popular in coastal erosion monitoring. Citizen scientists, who are members of the public, contribute to data collection and analysis, expanding reach and scope of monitoring efforts. Through citizen science programs, volunteers can participate in shoreline surveys, collect observational data, and contribute to erosion assessments. Engaging the public in coastal erosion monitoring not only increases the amount of data collected but also raises awareness and fosters a sense of ownership among coastal communities. 12. Sediment budget analysis. Understanding the sediment budget of a coastal system is crucial for assessing erosion rates and identifying sediment sources and sinks. By determining the sediment budget, scientists can identify imbalances and better understand the factors contributing to erosion. This information is valuable for developing targeted erosion management strategies, such as beach nourishment or sediment relocatio. End projects. 13. Coastal monitoring programs. Coastal monitoring programs are comprehensive initiatives that involve the systematic collection and analysis of data relating to coastal erosion. These programs often involve collaboration between government agencies, research institutions, and local communities. The data collected through these programs support evidence-based decision-making and the development of effective erosion management. Policies. 14. Digital Elevation Models, DEMS. Digital elevation models, DEMS, are three-dimensional representations of the Earth's surface, including coastal areas. By analyzing DEMS, scientists can derive valuable information about coastal topo. Graphy and identify areas susceptible to erosion. DEMS can be generated using various remote sensing techniques, such as LiDAR or photogrammetry. These models enable researchers to assess changes in coastal elevations over time, detect erosion hotspots, and evaluate the effectiveness of coastal protection measures. DEMS are essential tools for understanding the complex interactions between land,